Okay, so we're going to start with something that is, I suppose, new for Leaving Cert, which is correlation and I suppose scatter plots, which are kind of very closely related to that. So when we're looking at correlation and scatter plots, what we're looking at is a certain type of data, which is called bivariate data. Now, whether we remember that's what it's called, it's kind of neither here nor there. It's more about what it would mean. And bivariate data is data which has two connected variables. So we might look at, for example, if we were looking at a person, we might look at their height and their arm span is a common one, and whether there's a relationship between that. We might look at age and shoe size or something like that. So nearly two variables or two things that are related to the same data. So another example would be we might look at something that happens over a week. So one of the data points would just be the day of the week, and the other would be whatever it is that we're investigating. So the number of people at a bus stop each day, and we're taking into account the day is important. Okay. So that is bivariate data. It's important because we want to be able to represent both of the data points, and we're going to be looking at the relationship that maybe occurs or is that we can identify between those data points, okay, or how those different variables maybe weigh into that relationship. So correlation is our measure of that. So we say things are correlated is how closely related are those two data points. And we measure it on a scale from -1 to +1. So +1 being they are perfectly, completely correlated to each other, -1 being they are not correlated at all. And what it really means here is just how related are those two variables. So if we think of, for example, if I was doing, let's say, temperature is a common enough one. So we'll say temperature and ice cream. I think that's one of the examples anyway, but let's look at it here. So temperature and ice cream, for example. So if we were looking at that over a series of days, over a week, 2 weeks, over a certain length of time, and each day we look at what the temperature is and we look at the ice creams that were sold, we would expect that as the temperature goes up, that we would expect the sales of ice cream to also go up as well. And it would be safe to say here that the temperature is affecting that. The temperature is causing there to be more ice creams sold, and in the same way that more ice creams being sold would lead us to believe that the temperature is also higher. So the two are quite closely related to each other, and one is affecting the other. So we would say here this is probably a fairly good correlation. It's probably a strong correlation between the two of those things there. We could have other things, so let's stick with temperature, but let's say we look at the temperature each day and we say the time to get to school. Okay, so we're looking at what temperature it was each day and how long it took you to get to school. There may be a relationship between the two of those. There could well be a relationship. Perhaps if the temperature is good, you walk to school. If the temperature is not good, you get the car to school. That would be a very clear relationship between the two. In other cases, somebody maybe always gets the car to school, so the temperature is not going to affect the time that they take to get to school at all. So we can see there that it's not maybe as clean cut as like here it did affect it and it's the same relationship. There maybe is more that can play into that. So that's another thing that we would consider, I suppose, within our kind of conversation there a little bit. So looking at kind of how we work with that a bit more explicitly, with correlation, we're measuring the two variables and how related they are, and we're measuring that on a scale from -1 to 1. So we think about 1 as being these two variables are perfectly related. They go up by the same amount essentially each time. So if one goes up, the other goes up by basically the same amount, and they follow in the same kind of pattern the whole time. -1 means the same thing. They're perfectly correlated, but in a negative way. So rather than them both going up the way, as one increases, the other actually decreases, but they follow in a negative sense. The different types of correlation, we can kind of see pictures of them here, and this is working with the scatter plots that we're going to get into. So with a scatter plot, what we do is we look at each axis and we plot each data point. So we're taking those two variables, so say 14 degrees like we were looking at there, and maybe 14 degrees and there were 10 ice creams sold. I would plot that on my graph at 14 on this axis and 10 on this axis, and I would plot it there. I could do an X, I can do a circle, I can do whatever. And what we do is as we plot those different points across the different days, we would comment on how close our points are to forming a line. Okay, so perfect correlation is linear, straight line, nice, plots, everything just plots it nicely. Okay, and the closer we are to getting that straight line idea, we would say the stronger our correlation is. So one of the ways you can do that is to draw in a line like they've done there, which we would call the line of best fit, to draw in a line and kind of see how close most of the points are to that line. And if most of the points are fairly close to that line, that's going to suggest a stronger correlation. And the more points you have that are further away from that line, that suggests then a weaker correlation. So the key things with correlation are we have to say whether it is strong or weak. So we talk about the strength. So we'll do that first. So we talk about the strength of the correlation, and we talk about, I'll say, direction, perhaps. So for direction, that means whether it's positive or negative. So if we're asked to describe the correlation between two variables, we need to hit on both of those things. So is it strong or weak, and what direction is it going, positive or negative? And obviously we could have no correlation as well. Okay. As I've said, it's measured on a scale from -1 to 1. Could fall anywhere between there. No correlation would be 0. Okay, so no correlation is 0. We go up towards 1 then is perfect correlation, and that would be perfect positive correlation. And down towards -1, which would be perfect negative correlation. And anywhere between there, we kind of get a sense of where we're at. So I would say kind of from maybe 0.7 upwards, around about that, I would probably consider to be strong. We might have kind of medium in the middle, and we might have weak then down in the kind of lower numbers. So you kind of give yourself a kind of middle ground there to be able to describe the correlation. So you need that measure of strength and direction. The other key thing with correlation that can be really important is this idea of causation. And making that kind of distinction here that something being correlated does not mean that one is causing the other. So, for example, if a shop opens, an electrical shop opens, we might look at how many refrigerators are sold and how many laptops are sold. Selling more laptops does not cause you to sell more fridges. And similarly, selling more fridges is not going to mean that I'm going to sell more laptops. However, if it was a new shop, then perhaps both would increase because the shop is newer. Or we might just get more customers, so both actually happen to be higher. So there may be a relationship, because if I'm selling more of one, I possibly am selling more of the other, but one is not causing the other to be sold more. So looking at another example or two here, so this example gives us two tests on which 8 people scored different results, and we're trying to compare the results across the two tests. So we've started by plotting this on our scattered plot here, and we can hopefully see, like, say the first point we have here is 21 on the first test, 58 on the second test. That's this point in the middle here that I've highlighted. So 21 on test A, 58 on test B, and we mark it in. And what we can kind of see happening here is as I go from left to right, the points are going downwards, which would suggest that if people got a higher score on test A, they tended to get a lower score on test B, and vice versa. The higher the score nearly that they got on test B seemed to be a lower score on test A. So perhaps the two tests were in completely different subjects or opposite subjects, that people maybe were stronger in one and less strong on the other. So if we were describing this correlation, well, first of all, I'm looking at the fact that it's going downwards. So I think it's definitely going to be negative correlation. Then I need to consider whether I think it is strong correlation or not. Now, looking at the line that we've drawn in here, we can see with the way we've drawn it, there's at least 4 points that are basically on that line, and the other 4 points are quite close to that line. So I would consider that to be quite strong negative correlation there. Okay, that the points are not all together spread out. They're fairly close to that linear idea. Yes, they're a little bit away from it, but they're still fairly close to that linear idea. I might even give that a correlation of up in the 0.7s. Okay, let's have a look at some of the exam questions and then see the sort of things that they're kind of highlighting or pointing out in the exam settings here for these questions. So the first one asks us, for each of these different types of correlation to describe or show what those would look like on a scatter plot. So strong positive correlation. Well, positive correlation, first of all, means that as we go from left to right, it should be going upwards. So we need to remember that. Strong means we need to try and keep our points in a quite linear fashion. Not exactly a straight line, but fairly close to a straight line. So if I start maybe with 1 point here, I would be looking to keep my points in fairly close to a straight line idea there. So that would be strong positive. Strong negative is going to be very similar. However, instead of going up the way, we are going to go down the way. Okay, and just keeping that idea that if I drew a line through my points, that most of my points would be on or very close to that line. Last one then, no correlation. Well, no correlation should mean that my points do not follow any sort of clear pattern, that they're not moving upwards in any real kind of measure here. These points are all over the place. You've multiple points nearly on top of each other. There's no sense that it's increasing or decreasing. Let's look at another example. So they're giving us some scatter plots here and we have to match them to different correlations. So they've given us the different correlation coefficients, which is the measure of that correlation, and they're asking us which of the scatter plots would correspond to which. So let's look at each scatter plot first of all. If we start with A, it's going down the way, which should mean that this is negative correlation. The other two are going to be positive correlation. So immediately there's only one correlation that is negative, and that's the minus 0.95. So I'm quite happy then to say that that must be A. And that's quite a high measure of correlation for something that, from us looking at it, we mightn't have maybe gone with 0.9. There's still a bit of a ways to go to make that quite linear, but it's a strong correlation, I suppose, going from left to right. If we look at B, I would say B is more similar to that as well, perhaps even stronger. There's that sense that as it all increases, that it's increasing in a similar way. So I would put B as my 0.95 and C then as my 0.6. My points yet are largely spread out. If I draw a line, there's quite a gap between those points. None of them really are close to that line at all. They're asking us to explain why we picked the correct value for B. I would say that B is strong correlation. And I would say that B is positive correlation. And why do I think it's positive? Because it's increasing from left to right. Strong correlation and positive correlation because it's increasing from left to right. Okay, we have a question now from a deferred paper, so just a bit of a longer question, which is no harm to give us a bit of insight into the sorts of questions here again. So here's the example that I mentioned earlier. Liam and Ava are selling ice cream, and Ava wants to investigate the relationship between the temperature and the ice cream sales. And she writes down the temperature and ice cream sales for 14 days, and then she plots them on the scatter plot below. Okay, and this is for 12 of the days is what she has plotted already. There's 2 days here that she has not plotted that we have to plot ourselves, so let's do that. Temperature of 23 degrees would be here, and the ice cream sales that go with that is 500, so let's go up to around about 500 and mark in our point here. Let's do the same with 17 and 400, so 2 nice points I suppose to plot in, kind of nice easy ones. We're asked to plot and label the 2 points, which we've done. We are asked to describe the relationship between daily temperature and ice cream sales. So looking at it here, I would say that we're safe to say that as the temperature increases, the ice cream sales also increase. Okay, so as temperature increases, okay, looking at the graph here, I would say that's a fairly good and clear relationship that seems to be happening for most of the points, that as I go upwards in temperature, go across to the right, that I'm also going upwards as well. So I would even go as far as saying that that is strong, and we will say it is positive because both are increasing as well. So strong positive correlation. If we wanted to pick out which of the correlation coefficients we think it is, well, we've decided it's positive, which means it's not either of these two. So we have to decide between 0.2 and 0.8. I suppose, made the decision that I would see this to be strong correlation, so I would probably go with my 0.8 there. They're asking us now to circle the outlier on the scatter graph and give a possible reason for this outlier. So let's have a look at the outlier and what that could be here. So my outlier, I would pick this point here on its own. Okay, I suppose the reason that I would be kind of happy to say that that's an outlier, if we kind of think about what an outlier means, an outlier is a point that does not fit in with the rest of our data points. Okay, so a point that does not fit in with the rest of our data points. And that point there stands out quite a bit from the other data points. It's a high enough temperature of 19 degrees. However, the ice cream sales, it feels, does not match that temperature. So if we look, have they asked us to explain it? They have. A possible reason, we could say one reason is maybe they ran out of ice creams. Maybe they just simply ran out of ice creams and there was no more ice creams to sell. So even though the temperature was quite high, they didn't have any ice creams left to sell. Fair enough. Not much else they can do there. Okay, let's look at the next part. Work out the mean and standard deviation for the different ice cream sales. So let's start with the mean. We should hopefully remember that for the mean, we need to add all the points and we need to divide by the total number. We need to divide by the total number of points. We're only looking for these 7, so we need to add all of these together. So if I add all those together, I'm going to get 3010 over 7, which is 430. So my mean sale is 430. Standard deviation, we do entirely in our calculator. So you might want to go back and review that. It's a measure of how spread out the data is. So if we do our standard deviation here, I'm going to get 138.98. 138.98. So measure of how spread out our ice cream sales, 138.98 here. Okay. What would happen to standard deviation if the value for Sunday, which was the 147, was omitted from the calculations? Give a reason for your answer without calculating a new standard deviation. I would say here that the standard deviation would decrease. If we look at the one they're talking about, the 147 here in this list is entirely far away from the other ones, so it would decrease the spread of the data. So if we remove that one, then the data would not seem to be so spread out. Okay, so that's really all that we have, I suppose, for our normal distribution, for our scatter plots there. Okay, really important just to stay on top of the different types of question that are coming in there for us. So really kind of looking at what it means to be perfectly correlated, to be strong positive, strong negative, that measure of between 1 and -1. Can you pick or estimate a number that it could be? Can you recognize a certain type of correlation when you're looking at it? Can you describe it, making sure you describe the strength and the direction of the correlation? And that's really all that's going to come in. It is about kind of making those assessments and being able to make those conclusions based on the graphs and the data given to you.